Okay, so let's start then. So hi everyone, welcome in the first session of I hope a long list of sessions. So we had the 8th of January. Um, so we're gonna start by introducing the concept and the goal of our regular meetings. We're gonna introduce also everyone here in the meeting, and we also gonna talk about the structure of of the different meetings, the different sessions, and from there we're gonna start the first session. I'll start the first session by talking about basic algebra. We're going to go through the definition of sets, and we're going to discuss the common set. It's going to be really 101. We're going to go into the definition of groups, rings, fields, and polynomials. And we're going to also define some notations that we're going to often use. So I'm going to start with the introduction. So first, these meetings are going to be focused on of trying to formalize cryptographic primitives and cryptographic properties and cryptographic protocols in some languages. We're going to try to formally, we're going to make presentations about cryptographic protocols, but also we're going to study some tools to be able to do some formal verification, and we're going to try to intersect these two sessions. And in particular, in cryptography, we're going to study more the notions that I used in what called ZK for zero knowledge, and which is just a placeholder for more. We should use more like verifiable computation. I'll mix sometimes the different notions. And the goal is gonna be to make courses step by step that you can follow, and you can just learn the basics. You can just go from one session to the other, and we gonna provide. We're gonna do a certain structure, which is we're gonna start first by always introducing the maths using pen and paper. After that, try to make some implementations of the concept that we just learned in the pen and paper sessions. From there, we're gonna move to so the pen and paper math is gonna be really proving or giving at least the ideas of the different theorems and the different lemmas and the different definitions, making some proofs on paper. And when we implemented in normal, let's say, common programming languages like Python, JavaScript, or others, or Rust, we're going to try to formalize these algebraic objects, these lemmas, these definitions, mathematical definitions in a language like Rocq or Coq. I don't know how we're gonna name it. Maybe Lean, let's see in the future. But we are more focused on Rocq because it's where our expertise is. And we're gonna make the proofs in Rocq or in Lean. We're gonna make the proofs of the lemmas and the theorems that we just sketch on paper after. And from there, what we would like also to do is to have some to invite some industrial users, in particular for people doing security audits, for instance, where we analyze some bugs that can be found in some implementations, and we explain the maths behind. So that's the main goal and the main ideas behind these sessions. It started because Guillaume and I wanted to share the knowledge that we've got in cryptography and formal verification, and we think that it should be free and accessible to everyone, and people have been asking for it. So we just gonna publish it freely on YouTube or any other platform. Let's see in the future. So it's gonna be not only one session, not only 4 sessions. It's gonna last for months. So from here, I think we're gonna start by introducing each other. Maybe we should have started with this. I can start with myself. So I'm Danny Williams. I'm a cryptography engineer at Owen Labs. Owen Labs is a company focusing on programmable cryptography. We incubated initially the Mina protocol, but we also work on different projects like the O1VM, O1JS that can be used to write ZK smart contracts for Mina. But also we're working on what we call a project Untitled. And besides that, I'm also the co-founder of LeakIX. LeakIX is a company where it's a cybersecurity company. We scan the whole internet 24/7. We identify services running on the internet, and we try to make what we call plugin to find the vulnerable instances of these services on the internet. I've got mostly a background in mathematics, algebra mostly, and logic, and also in type system. So that's it for me. I'm gonna give the mic to Guillaume, Andrea, and Antoine after. Now.
Yes, thanks, Danny, for the introduction. So, I can present myself. So I've worked mainly on formal verification, done my PhD in this domain, and I specialize in particular in verification using the Rocq proof system, and working on verifying implementation for cryptocurrencies. I worked a lot for verifying the Tezos protocol, and now for solidity smart contract on the Rust programs. And I founded the Formulon company to apply these techniques, and we provide services to crypto protocols who want to verify their code, and especially one of the hot topics these days is zero knowledge systems that we will cover in these classes. Yes, so maybe Antoine, so you can present yourself.
Yes. So my name is Anton James. So I work at Formerland with Guillaume as an intern. So I'm learning about formal verification, and we also do sessions with Danny to learn about cryptography as well. So as he mentioned, this idea came up because we were doing meetings, and basically people were asking for knowledge about zero knowledge and cryptography in general, and as well formal verification. So Danny posted a tweet about this, and he was there are a lot of engagement for this kind of topics. So we started the sessions. For my background, myself, I'm a programmer. So I mostly worked with the Java language, but I also worked with other languages such as Python mostly, and also I'm learning Rust at the moment. So at the moment as well, I'm doing a master's degree in cybersecurity and management, and I'm writing my thesis for my master's degree, which is going to be focused on formal verification, also a bit of cryptography, and I'm also gonna introduce the other principles of blockchain security, which is gonna be fuzzing, so fuzz testing, and symbolic execution as well. And on the side of that, I'm also launching a platform for people to learn how to create POCs, so proof of concepts, for mainly cybersecurity audits in the blockchain fields. There are a lot of platforms where you can participate in audit contests, and most of the time you're required to bring a POC when you submit a vulnerability. So, and there is a lack of educational content to really level up on this topic. And so this is going to be launching early of this year. So I hope that people will be able to use it and give me their feedback. And I can just give the mic to Andrea so he can present himself as well.
Yes, thank you. I am Andrea Del Mastro. I am an intern at Formalland. I graduated in artificial intelligence, and I'm in Formalland trying to cross the boundaries between artificial intelligence and formal verification. So we are working on trying to apply LLMs to formal verification tools. And so my expertise in the field of security and formal verification of security protocols is not that much, but I'm here mostly in quality of auditor to give feedback to the group. So.
Perfect. Thank you, everyone. And also, what also we want to do in these sessions is to make something interactive. Also, if you're watching this video and want to attend some of this meeting, just let us know as a student or as a speaker. We really want to have more people coming. And we want to make it accessible to everyone, always free. So that's really our goal. So yeah, during the presentation, Guillaume, Andrea, and Antoine, feel free to just stop me and ask questions. So let's start. Let's have fun. So I think I said it, but we're gonna start with some algebra, basic 101 algebra. Why? It's because a lot of concepts in cryptography relies on algebraic objects, and the security, the bugs that we can find in some implementations are often related to some properties, some mathematical properties of this object that are not respected, or there are some maths behind. So it's important to really understand them, to know what we are working on, what. Hey, Andrea. We're just waiting for you. We're gonna start again. Okay. So sorry if we're gonna start again. So as I was saying, structures, the algebraic objects that we work with in cryptography, it's very important that we really understand them, especially when we implement them. As I said, most of the bugs that I've found are related to the algebraic properties. So I'm gonna do basic math, so maybe just reminders. It's gonna be a pen and paper session this time. Next time is gonna be an implementation. So we're gonna implement in a real programming language. Oh yeah, and you're gonna see I hate slides, so I'm always gonna write everything. So 101 algebra. First, basic question, what is algebra? It's mostly studying structures over a set of values. We try to find the relation. We try to define relations between values in a set. So there are different structures that do exist. There are what we call groups. Oh, I'm not going to use the yellow. Let's use the purple. So there are what we call groups, rings, fields, polynomials. Polynomials is just a kind of, it's a ring. There are many others, but mostly what we're going to study here, top of my mind, are going to be these ones. So I'm going to make some reminders regarding sets that everyone, that I think everyone know, and some notations. So sets are just a set of values. In a programming language, you can consider that it's a type, and we're going to see later when we're going to implement in Rocq or others how we embed that in a programming language. So like the naturals are only the elements that are the positive numbers. You've got the integers. So the notation for the naturals is called n. For the integers, the integers are simply the negative values. So minus 4, 0, and the positive values. Yeah, we don't include it, but anyway, you understand what I mean. And we've got other sets like the rationals. The rationals are all the fractions, so all the values that you can write p over q, such that p and q are integers, and q should be different than 0. And also the real numbers, we all know them. We're not going to use it here because it's not going to be useful. I don't know why I mentioned it, but these are the sets, and you can have a set. I don't know, like if you take the set S with 0, 1, 2. What we're going to do is we're going to try to add a certain structure on top of it. And we're going to try to make have some properties also using these relations. So we're going to start first with also some notations. I hope it's okay for everyone. We're going to use very often these symbols, which means for all they exist, some value, etc. So for instance, this means for all x for all naturals, they exist y in there is another natural number such that let's say for all x they exist another natural such that x plus y equals z. And here is just the addition on the naturals. So just try to get familiar with these notations. So it's like a E reverse. It's what we're going to use to define the different properties. So that was simply for the notations. So let's start with groups. What is a group? Let's first have a look at some examples. Like when we take all the integers, we've all studied that, if you take 3 and you take 4, all of these two values are in Z, and you can do a certain operations on them. You can, what we call in our language, just add, and we always use this notation of plus. And it's equal to another value, which is also an integer. And we also have a... okay. So in a sense, we've got an operation that we've got a function plus that goes from Z that takes a tuple in Z and returns another integer, and it takes an element x, y, and returns certain value x plus y. And on the integers, you have some properties, like if you take any element in x, in Z, if you take any element x in Z, and you take another. Let's start first. Sorry. Let's start first with the identity. So in this set, in the integers, you've got a certain number, which is 0. So 0 is an integer, and you will agree with me that if we take any element, any integers, if we do x plus 0, is going to be equal to x. So it's, in a sense, 0 doesn't have any particular effect on the addition when you want to add something. If you also so on the right, so if you add on the right, but if you add also on the left, it also gonna be equal to x, and that's for all elements in Z. So I'm gonna try to maybe look. I'm gonna write. I'm gonna make like a formal. I'm gonna make here examples, and here I'm gonna make abstract, maybe abstract definition. So here I'm gonna write Z for the integers. So as I said, for all x in Z, x plus 0 equal x, and 0 plus x equal x. And so if we take any set, I don't know, we're going to use the notation G. 0 in a sense here is, we can say that there is a certain element, let's call it y, in G, such that for all x in G, we've got x plus y, which is equal to x, but also y plus x equal x. And what we're gonna use a certain definition for this. We're gonna say that y is an identity element. And very often, we're gonna note it as 0, and sometimes we're gonna use a subs. We're gonna write also the G to mention that it's related to the set G. What we also do, what we also have is for every element in Z, for every element in Z, for every integers, we can also find another value such that x plus y equals 0, and also y plus x equals 0. And very often we call it minus x, so it's what we call the opposite. So that's one property. So the second property is for all x in G, there exists another element in G such that x plus y equals 0 and y plus x equals 0. And we say that y is the opposite of x, noted minus x. So I think it's clear. I think it's pretty clear until now, everyone. If I'm too slow, just let me know. And what do we have also? Yeah, Guillaume?
Yes, I'm wondering, you are taking a Z as an example.
Yeah.
I wonder what can be other examples of groups. Is it only numbers?
Sure. So good point. So here we used so all the notations, so all the symbols that we use are very important. So here, why I'm trying to, I might be slow, but it's because it's very important in the future. We're going to use sometimes what we call the additive notation, or sometimes the multiplicative notation, and we're going to move between all of them in more abstract group. So here the relations that we're looking at is the plus, but also a second example could be the rationals number, so the fractions. So if you take the rationals, so it's, as a reminder, the rationals are all the fractions. Let's take, for instance, I don't know, 1.5 on the right, 1.5, like this. And if we use the multiplication that we're going to use as a dot, we can always we can find another value, which is in this case 2, such that it's equal to 1. And the same thing is if we take on the left, we also have 1. So in this case, we can say that here it's x, here is y, here is the identity. So y, x, and we have the same, if we take the analogy with the plus here, if we just replace the notation of the plus with the times, if we take the multiplication, we've got exactly the same properties. So if we just remove 0. So if we take all element x in the rationals except 0, we're going to use this notation with subscript 0. We can find a certain value y, which is also not equals to 0, such that x times y equals 1. And also the same thing, y times x equals 1. And same properties. If we try to check the identity property, if we take any element x in Q0, if we do x times 1, it's equal to x, but also 1 times x is equal to x. So in this case, the identity is 1. And the notation for the relation is simply a times, a dot. We can use times if you want, but very often we just use dot. Does it answer your question, Guillaume?
Yes, thanks.
So what we also want to have, what we often gonna work with, is what we call commutativity. So if we take any value in the integer, so we can switch z with q if you want, for all x and for all y in z, we've got x plus y equals also y plus x. But also what you've got is you've got, if you take any three values, if you do x plus y plus z, it's exactly the same. If you do first the plus on these two values, it's exactly the same than if you do the addition first on the two last values. You get the same result. So again, just example, if you take 3 plus 4 plus 5, exactly the same if you do times 3 plus 4 plus 5. That's pretty obvious. And so that's called the associativity property. Associativity. And here is the commutativity. Commutativity. And I think from there, I think I'm not missing anything. Do you confirm, guys? Yes, I think. So we're going to get then to the formal definitions of a group. If there is no question, of course. Nope, no question. So we're going to define what's a group. So we just take like S, or let's say G. Let G be a set. And let's take a certain operations that we gonna call it plus in our case. So let plus be an internal operations that takes two values in G. We gonna have some properties on so a certain relation, I'm gonna write an internal operation on G. We say that G is a group. We're gonna even use, sorry, I'm gonna add also another element, and let be, we're gonna use the notation 0. I'm gonna subscribe by G, an element of G. And we're gonna say that, we say that G, and we're gonna use a certain notation this way, 0G is a group if we have different properties. So for all x in G, if we do x plus 0 G, it's equal to x. If we do 0 plus x, it's equal to x. We also have that they exist. Oh, sorry. For all x in G, they exist y in G, such that x plus y equals 0G. We also have the associativity. So if we take any element in G, any element y in G, and any element z in G, if we do x plus y plus z, it's exactly the same than if we first apply on the left, on the right, and after that we apply on the left. So I'm gonna name it, so associativity, just gonna rewrite it. And here it means that, so I'm gonna use the notation 1, 2, 3. So that's for the different properties. And 1 plus 2 means that 0 is, we said that 0 is the, if we've got these two properties, we said that 0 is the identity of the structure G0 G plus 0G. And we can even go further. So that's for the definition of a group. I think I didn't forget anything. So the existence of an opposite. Oh yeah, and to say that for the value, we say that the value y is the opposite, or also we use or the inverse. Why the inverse is because when we use the rationals number here, we use the inverse. So 2, 1 over 2 is the inverse of 2 in English. And so we also use this word. So the inverse and the identity. So plus can be also y. If we use the notation plus, we're going to call it the opposite. If we use the multiplication, we're gonna often use the term inverse. And some examples. Maybe I'm gonna describe maybe another property, additional property that we can have. I described it above, but I'm just gonna recap. Additional properties. I only have one in my mind, which is the commutativity. Commutativity, and it's for all x in G, for all y in G, x plus y equals y plus x. So it's an additional property. So we're gonna see, I don't know if we're gonna see, but not all groups are commutative. So there exist some sets G and some, it means that there exist some sets G and some operations plus and some elements 0 that are also in G, such that the operation is not commutative. It's not going to be useful in cryptography. I think we never use any top of my mind, so we're not going to use it. But that can be a good exercise to find one. And also, we also use the term abelian because it's related to a mathematician for commutative group. So commutative groups is just a group that, in addition to having these two properties, also have the commutativity property, and we also call them abelian. Bit of history. All of these notions come from the 20th century, late 18th century. The notion of groups. We were already studying all the numbers, and we knew the numbers for a long time. But we tried to formalize at the end of the 19th, beginning of the 20th century, all of these terms. Everything that we're going to study is mostly 20th century, mostly. A bit of 19th century also, if you like history of mathematics. Any question from here? It's already taking a lot of time. No. Okay, so some examples. Some examples that everyone knows. So we studied Z, so the integers. Also, we studied the rationals. You also have the real numbers. So the real numbers are all the rationals, but also the elements that cannot be described as a fraction. Also, if you remember some math courses, the complex numbers. What is not a group? Any idea? Andrea or Antoine? That is not a group, a set that we saw before. That is not a group. Or Guillaume? We saw another set below.
The natural number.
Yes, exactly. So the natural numbers, n, is not a natural. It's not a group. Why? Because if we take 3, it's in n. Also, we've got 0, which is in n. But we don't have the value -3. It's in z. It's an integer, but it's not in the natural. So we don't have the properties that's for every element in the natural numbers, and for every natural numbers, we don't always have an opposite. And another group that we're going to use very, very often, we even going to use it, it's mostly the one that we're going to use, is, do I have to remind modulo? Yeah, I can remember. I can make a quick reminder. Another group is another example of group. Another example of groups. So if we take, I don't know, I'm going to take 0, 1, 2, 3, and 4. I'm going to take this set of 5 values, and I'm going to use the operation that I'm going to call +5. You're going to see it's very important. And I'm going to use also 0, and I'm going to call it 5. I'm going to use a subscript 5. +5 is simply going to be, I'm going to write it S, or maybe let me write it this way, Z5. You're going to see later. So if I take any element, if you the operation +5, which is going to be also an internal operation, is going to be the operations that take 2 values and do x plus. This is the addition on naturals, on integers. So the one that we all know. Mod, we're going to take the modulo mod 5. So quick reminder, if we take, so examples, if we take 3 plus 4, is going to be 3 plus 5 mod 5, plus 4, sorry. And you don't tell me. 3 plus 4, 3 plus 4 is equals 7. The modulo is going to be equals to 2. So you see that modulo 5, you just take the rest of the division by 5. So it's equal to 4. If I take, I don't know, 0 plus 3 or 1 plus 3, mod 5 is going to be equal to 4. So 1 plus 4, 1 plus 3, etc. And as a small exercise, or you can try to convince yourself, is that every time we gonna take any element in this set and we're gonna try to make the modulo, which is exactly the concept of the modulo, is always to come back in a value that is smaller than this value here. And so we can therefore say that if we take any natural numbers which is greater or equals to 2, if we take the notation, if we take the set 0 until n, and we take the addition modulo n, and we take 0, it's going to be also a group. And I'm very often going to use this notation Zn. And in particular, just because I'm very often going to use this notation too, in particular, if n is a prime number, we use the notation Fn for Cn. We're gonna see it later. Another kind of group. Oh,
Just to make sure, so the reason why n isn't a group is because there isn't an inverse element, right?
Yes, exactly. An opposite. Yeah, an opposite or even just an inverse. So in this case here we n plus 0. If we use the notation with the plus, so the addition on the naturals is not a group because the opposite, the normal addition that we use on natural numbers, if we want to get the opposite of 3, which is -3, -3 is not an integer, a natural number.
Okay.
Do I have to remind what is a prime number, or it's fine? I can, if someone wants, of course. No? Okay. And another type of group, we're not going to see it now, but we're going to see it later. So I wanted to explain another type of group. I'm not going to describe what they are at the moment. But another type of group is what we call the elliptic curves. Very, 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 very important. We're gonna see it later. It's been already like a long session, so maybe we can stop for today, and next time we can do another session on the other kind of structures. We're gonna describe what are rings and what are fields, and you're gonna see that a bigger we take the set. We always take like a certain number of elements, a certain number of a certain set, and we try to structure them in a certain way. We try to make some relations between the elements. So here we added a simple structure, which is simply the existence of an identity element and also the associativity. But we're going to see that we can add even more properties on it, and even more operations. So at the moment, it's only one operation, and we're going to see later that we're going to add another kind of operations. So yeah, let's stop for here.
Yeah, but maybe I had a question also is why do we do as group definitions? And yes, it seems also that some mathematical elements are actually very general, and people found a nice structure that is common to everything.
Sorry, I didn't get the question.
Yeah, it was why do we define the notion of group? Because we already have the addition, for example, for integers.
Mm-hmm. Because we're gonna study a certain kind of groups, which are gonna be the elliptic curves, and the elliptic curves are a certain kind of group. They are not something else that we need. So we first start with the group, and after that we're gonna go in other structures. Does it answer the question?
Yes. Yeah, thanks.
So let's stop from here. No programming here. In the next session, we're gonna do some. We're gonna suggest some lemmas to proofs, some also propositions. Here, let's maybe let's go deeper later.
Thanks.
So Yeah, thank everyone for watching. I don't know if anyone has a comment. Maybe next week we're gonna do another session.